Welcome to lecture series on electronic science under EPG Pathshala. We are starting with a new course, Wakedale and Verilog. Basically, this course is intended for learning the hardware description language. This language is normally used for designing digital ICs. In many cases, whenever we start with designing any digital system, there are different ways we can design it. The first simplest method is use traditional digital ICs, those are available, which are SSI, MSI, LSI and several other combinations. But the circuit complexity can increase as you increase the size of the application. There is another method, user can go for designing the circuit with the help of programmable logic devices. These programmable logic devices are another better option. In addition to that, user can go for designing his own IC, which is usually called as custom IC. Now, all these design applications, they have their own advantages and disadvantages. In this course, we will begin with learning the syntax and semantics of the language normally required for designing the digital systems. Whenever we start with designing the digital system, the first important part that we have to talk about how the IC could be designed. Let us look at it as a standard product design life cycle. It begins with a design specification. You have to undergo several steps and then come with the final product. The same method can be adopted and we can definitely go for using some kind of sophisticated electronics design automation tools or CAD tools, which can support the designer to design the IC, which will definitely remove the complex efforts or maybe the complexity in the design, and then you can get the product with the great ease. Whenever we talk about such kind of CAD tools, we need to think about different stages in design. It starts with the specifications, then come with certain pilot design, test it either using hardware prototype or you can go for simulation. After simulation, verify the result, and if they are matching with the design, then we can say that our final product is implemented. If not, then we can go back and vary certain parameters in the design and then come up with the final product. In this session, we will be focusing more on learning the digital system design process, starting with the simplest or the traditional design process, and then we will go to the sophisticated design process described under CAD tools. Let us define the learning objectives of this module. After learning this module, you will be able to understand the importance of digital system design. This module will also provide various digital system design options right from fixed function ICs to programmable logic devices, that is PLDs. Further, basic design process will be discussed to learn about product design cycle. This module will discuss the digital design process used in CAD or EDA methodologies. Let us now begin the journey in the digital system design process. Digital system design is the science of organizing information, defining operations, accepting inputs and generating outputs using discrete quantities. In a system, there is a function that translates inputs to outputs. Digital ICs are the backbone of modern electronic gadgets. Designing of digital system involves designing of the hardware as well as implementing the required software. Hardware mainly looks into handling analog, digital or mixed signals. Modern technology offers many new features and aspects to digital systems. Digital system is one such data technologies which utilizes discrete values to represent the information, unlike non-digital systems where information is represented using continuous values. There are two types of signals, analog and digital. A digital system applies digital signals for functioning. An analog signal is any continuous signal for which the time varying signal is the representation of time varying quantity. It takes any value over a full range of voltage or current in a continuous manner. A digital signal utilizes discrete or discontinuous values. The information is represented by discrete values such as 0 or 1, low or high, true or false, on or off, etc. These signals take up only one of the two discrete values. Digital systems offer many advantages over analog systems. These are: first one, reproducibility. As the output of digital systems, unlike analog systems, is independent of temperature, noise, humidity and other characteristics of components, the reproducibility of results is either high in digital system than analog systems. The second advantage is ease of use and design. Let us now discuss about it. The greatest advantage of digital systems is that ease of use. The design of digital systems which require use of Boolean algebra and other digital techniques is easier as compared to analog designing. The third advantage is flexibility and functionality. The function or operation of the digital system can be implemented using different logic functions and can be changed according to the demand of the situation. It has ability to adopt changes to provide flexibility to the designer. Various ICs are available and they fall under various logic families. Fourth feature is programmability. Digital systems can be used for different applications by simply changing the program without any additional changes in the hardware. We normally use hardware description languages for this purpose. Next advantage of analog system is the speed. The switching speed describes how many times the inverter can change from 0 to 1 and back. Advancement in IC fabrication technology led to faster and faster switching in gigahertz to terahertz speed. Another advantage of digital systems is the cost. The cost of the hardware gets reduced by use of digital components, and this has been possible due to advancements in IC fabrication technology. Next advantage is the size. All digital circuits are designed and manufactured in an integrated form. All the circuit components are placed in a single chip. Hence, the size of the system is very small. The most important advantage of digital systems is that it can provide you a secure transmission and processing. Digital signals can be used for secure transmission of information using encryption and decryption techniques. Transmission is at higher rate and with a wider bandwidth. It is more secured. Next, the bandwidth requirement. Digital signals typically use less bandwidth. This is just another way to say you can cram more information, that is your audio video, into the same space. And let us talk about last but not the least, memory capability. With their memory capabilities, digital systems can be employed for computing, calculators, telecommunications, watches and other devices. Let us compare analog systems with digital. The first parameter is the signal. Analog signal is continuous, whereas digital signals are discrete in time. The second parameter for the comparison is the wave. In analog, we deal with usually sine wave signals, whereas in digital, we deal with square wave or rectangular wave signals. The third parameter is representation. Analog signal is represented using continuous range of values, whereas digital signals are represented using discrete or discontinuous values to represent the information. Let us now talk about an example of analog system. Let us say some analog meter or analog electronic devices, whereas in digital system the examples are computers, CDs, DVDs and other digital electronic devices. Next parameter for comparison is recording technology. Analog signal records the waveform as they are, whereas digital signals samples the analog signal and records the sampled value. The next parameter for the comparison is data transmission. Whenever we are using analog signal for the transmission, there is a deterioration by noise, whereas digital systems are not affected by the noise, they are immune to the noise. Let us consider the next parameter for the comparison related to the response of analog system to the noise. Noise definitely affects the accuracy of the analog system, whereas digital system accuracy is not much affected. Let us move on to the next parameter, that is flexibility. Analog hardware is not flexible, whereas digital hardware is flexible in implementation. The next parameter for the comparison is errors. Due to pointer and scale arrangement, there are considerable amount of observational errors, whereas in case of digital systems, the instruments are free from observational errors like parallax and approximation errors. Let us consider an application of analog system, that is a thermometer, whereas digital systems the example could be PCs and PDAs. Let us now talk about a parameter called bandwidth. Analog signal processing can be done in real time and consumes less bandwidth, whereas digital systems consumes more bandwidth to carry out the same information because it is usually sampled. Let us now talk about the memory capacity. Analog signals are stored in the form of wave signal, whereas digital signals are stored in the form of binary bits. The next parameter is power. Analog instruments consumes large power, whereas digital instruments consume negligibly less power. Let us now talk about the cost. Analog instruments are usually low cost and portable. But when we talk about digital instrument, the traditional digital instruments are little bit costlier as compared to analog, and they are not easily portable, except nowadays we have the convergence of technology which is bringing the TV, recorder, camera, everything in a mobile device. All mobile devices are portable, but otherwise the traditional instruments are not that easier to transfer, and definitely cost is little bit higher. Next parameter is impedance. The impedance of analog systems is low, whereas in digital system it has higher impedance of the order of 100 mega ohms. Let us now talk about the last parameter for the comparison, that is about errors. Analog instruments usually have a pointer and scale arrangement, which gives a considerable observational errors, whereas digital instruments, they are free from these observational errors. Digital hardware has seen rapid expansion and improvements in last 3-4 decades. The number of transistors in a single chip has grown exponentially and contains millions of transistors today. Moore's law states that the number of transistors in an IC doubles approximately every 2 years. This law is named after Gordon Moore, the co-founder of Intel and Fairchild Semiconductor Industries. As the IC became smaller, cheaper and faster, it became more and more capable of handling a wide range of applications other than just computing, like control, communication, medical, space and defense, etc. Digital systems are mainly used for storage, processing and transmitting the information. Larger the application, more it became complex in designing the digital system. The simplest way to deal with complexity is to think about the circuit at the abstract level and use design software tools to obtain low level implementation. The best way to design complex system is to keep the designer away from the tedious details of device level implementation and focus on design alternatives. In order to build the digital hardware for the customized application, there are ample device technologies to choose from. Off-the-shelf standard ICs like SSI, MSI, LSI, simple programmable devices to full custom devices. Standard ICs contain small parts with fixed and limited functionality and physical configuration. Each standard IC contains small and simple circuit and performs simple operation. As the IC technology improved, the number of devices and functionality per chip increased. Then this method became inefficient to use. In addition, none of the design softwares utilizes the off-the-shelf ICs, SSIs and MSIs, and thus automation in design is really impossible. As the programmable devices are capable and less expensive, the designers prefer this option over SSI and MSI ICs. There are two types of PLDs: simple programmable logic devices, that is SPLDs, and complex programmable logic devices, CPLDs. There are three possible devices under SPLDs. It includes first, programmable read-only memory, that is PROM, in which OR plane can be programmed. Second, the programmable arrow logic, in which an AND gate can be programmed. C, programmable logic array, PLA, in which both AND and OR plane can be programmed. Effectively, if you look at it, either AND or OR plane or both can be programmed, keeping one of them fixed or a variable. In the sophisticated way of customization, it involves creation of tailored mask and fabrication of pattern layers. These layers can be customized for a particular application. This process of customization is expensive and complex and can be done in manufacturing foundry or fabrication plant. These devices are called application specific ICs, that is ASIC. There are three types of custom design ICs: full custom ASIC, standard cell ASIC and gate array ASIC. Let us now understand the general design process. The development of any product requires certain steps must be performed in a proper order. Let us now understand the general design process. The development of any product requires certain steps must be followed. Let us study a typical product life cycle. The development of product follows an analysis, design, implementation, testing and deployment cycle. For a simple system, a one-time pass of cycle is sufficient, but for a complex system, it is necessary to repeat this cycle multiple times around the life cycle. In the analysis phase, the requirements of the desired products are clearly obtained. The main purpose of requirements is to state what the system will do. These requirements of the products in the general form are converted into detailed specifications. Specification would give exact requirement in quantitative terms. For example, the specifications of required ICs would include size, speed, power dissipation, functionality, etc. In the design phase, a conceptual model of the product must be built. The conceptual model defines as much abstraction as appropriate. At this stage, the design involves dividing the system into modules or components. During this phase, it is possible to estimate performance parameters, cost and schedule. The outcome of the design phase is to generate the block diagram and data flow graphs of the system. The preliminary design includes the overall top-down approach and hierarchical structure. The next phase of product life cycle is to develop an implementation of the system. The top-down design approach facilitates implementation of subcomponents simultaneously. At this stage, one may use simulator. One major advantage of simulation is that many initial designs are now implemented using hardware and software. Simulations provide a quicker way to implement the initial product on simulator than constructing a physical system. Because of higher cost and long time required to create hardware prototypes, rapid prototyping is an important stage in early stage of product design. During the testing phase, the performance of the system is evaluated. Debugging is an important step in testing and validating the basic functions. Further, measurements are carried out to optimize the performance of the system. Simulator can model the behavior of hardware or software systems. If both hardware and software are simulated together, the simulated time will be slower. Once the tests are successful, then one can deploy the product. If there are any new requirements or features, those could be corrected for any mistakes or maybe can be optimized for speed or size or a power. It is then necessary to undergo additional loop around the life cycle. Let us now discuss the basic design loop used for digital system design. The basic system design process consists of a sequence of tasks. The basic design loop begins with the design concept or an idea of the system to be designed. As the first step, the requirements of the system are clearly defined. These requirements of the system in the general form are converted into specifications. Specifications would give exact requirements in a quantitative terms. For example, the specifications of desired ICs would include size, speed, power dissipation, functionality, etc. Once the detailed specifications of the system are obtained, then it is possible to generate initial design. The designer's knowledge, skills and intuition play an important role in generating the initial design. The initial design must be tested before implementing the hardware. The initial design can provide conceptual model of the system. Simulations provides quicker way to implement the initial product on the simulator than constructing a physical system. At this stage, the designer must evaluate, verify the result of the design. Then the design should be further tested for applying test data or stimuli at the input and determining the output so as to verify the design as per the system specifications. If there is any error after simulation, then the design must be modified to remove the error. The modified design is again tested by the simulator so as to evaluate and verify the system parameters. Let us now summarize the basic design loop. The digital system design process begins with the design concept or an idea. Once you have an idea, the idea must be converted into the requirement and designer must transform requirement into the actual specifications. From these specifications, one initial design or the model must be created. Once the initial design is ready, it must be tested. Now, in order to test this, first what you need to do is either physically design the hardware, so build a prototype or do the simulation. Simulation is easier way, so simulations are carried out. During the simulation, you would be providing some typical inputs. Once these inputs are given, the desired outputs will appear. These outputs will tell you the performance of the circuit. If the performance of the circuit is okay, then you can say your design is fine. If there are certain changes in the design are to be done, then you have to remodify the design, go to the synthesis, build the model again and verify. So, this is basically a complete simple digital design process. The basic design loop discussed in the previous section helps the designer to test his design at conceptual level. In real life, the designed system must be implemented in hardware at every stage of design. This procedure is time consuming and involves higher cost for implementation, which may not be always possible to implement. Availability of various computer aided design, that is CAD tools or electronic design automation EDA tools have provided digital system designer a new approach to implement their design. These tools are used to aid the digital system designers to perform different design tasks. These tools provide a convenience to the designer to generate accurate and fast designs. The digital design process begins with defining the exact digital system to be designed. As the first step, requirements of the desired system are clearly obtained. These requirements of the system in general form are converted into detailed specifications. These specifications defines functionality, number and behavior of input and outputs, speed, power, etc. Once the detailed specifications of the digital system are obtained, then it is possible to generate initial design. The designer's knowledge, skills and intuition play an important role in generating the initial design. The CAD or EDA tools can help the designer at this stage to generate the initial design. The formulation of description of digital system can be done with the help of design entry tools. There are 3 design entry tools: truth table or waveform editor, schematic editor and HDL, that is hardware description languages. One can use either VHDL or Verilog language to enter the design in the editor. The next step in design process is the initial synthesis. Synthesis is the process of converting design entry information of the logic circuit into set of logic equations. The synthesis CAD tools helps the designer to generate logic functions required to implement logic circuit automatically. Once the initial synthesis is complete, it is necessary to verify the circuit function of the design using function simulation. It simulates the circuit function using the logic function obtained from the synthesis and the test inputs. The output of the simulator can be verified using either obtained truth table or timing diagram. If the output of the logic circuit is not as per the expectation, then the design must be modified. The synthesis, simulation, redesign steps must be repeated till the correct design is obtained as per the requirement. Once the functionality of the correct design is obtained, the next step is to use logic synthesis and optimization tools. This stage will help the designer to work on parameters like speed, cost and device technology for the implementation. Logic synthesis tools can be technology dependent or independent. If the synthesis tool is technology independent, then the optimization is independent of the resources available in the target chip. For technology mapping synthesis tools, the optimization is done using the logic resources available on chip. Once the logic synthesis and optimization is done, the next obvious step is to design the logic circuit using available logic resources. The physical design performs the 2 basic operations: placement and routing. Placement of the logic functions in the optimized circuit in the target IC and interconnecting the components in the chip, which is popularly known as routing. Once placement and routing in the physical design is complete, then the final stage of design is carried out through timing simulation. In timing simulation, the propagation delay of the logic circuit is evaluated and verified with expected design parameters. If the timing characteristics of the digital systems do not match, then designers must redesign at physical level. During the redesign process, optimized placement of the logic components and routing is reworked. Once the timing characteristics are obtained as per the design, then the design is finally implemented into the chip. Thus, we get the design of desired digital system. Traditionally, hardware software are developed independently and integrated later. There is a very little interaction between hardware and software before system integration. So, hardware software co-design improves overall system performance, reliability and cost effectiveness. Co-design concepts are more popular for designing digital hardware in system on chip, that is SoC applications. The design process begins with obtaining system specifications as usual. After analysis of the system, it might be necessary to partition the system further into subsystems or components. The hardware, software and interface systems are separately designed. This partition helps the designer in determining the best implementation for the system through iterative partitioning technique. Partitioning applied to the modules to best meet the design criteria like functionality and performance goals. At each level, it is necessary to carry out synthesis, hardware, software and interface synthesis is carried out for refinement of specifications. In the next stage, all the partitioned modules are simulated and integrated to see whether the required design objectives are met. In hardware, a model can describe a system in the behavioral, structural or physical domain. The software layer is very close to hardware and hides the hardware details and provides an abstract and portable view to the designer through virtual machine. Validation methodology ensures that system implemented meets the initial system requirements. If the final outcome is not as per the requirement, then another hardware software partition is carried out to handle this variance. This is the way how hardware software co-design based digital system can be implemented. Let us now summarize the things that we have studied so far in this module. This module is basically designed to understand the importance of hardware description language like VHDL and Verilog. Before we could design the IC using hardware description language, we have started with identifying the importance of digital system in today's world. We have compared the analog systems with digital, discussed many applications and advantages of digital systems over analog, and then later on we have started with the design process. The designing of digital system begins with a simple model. Now this model is based on the general model for product life cycle design. Now whenever we think about designing any product, there are three options those are available for the designer. He may choose a traditional method of design wherein he can implement the design with the help of the standard ICs those are available off the shelf in the market like SSI and MSI. There is a second option that is available wherein the designer can go for programmable logic devices. He may choose either SPLD or a CPLD. The third option that is available is design a custom built IC. Now this customer requirements can be very easily built into the IC, and this is well supported by the hardware description language, where user can think about building a system on chip. So this is a complex system that could be implemented, and several CAD tools or EDA tools can be used for implementing such kind of a design. Now we have started with a simple concept of designing a system. So the system design started with an idea or a design concept. Then this concept, that is the requirements of the system, are converted or transformed into the specifications. These specifications will definitely give us certain input for designing a circuit, and this model can have certain number of inputs and the expected output. Now designer may build the circuit or he can do the simulation. In this method we are thinking about implementation using simulation. The simulation tools can help the designer to get the system design quickly and easily. Once the simulation results are obtained, user can test or verify whether the system is performing as per the expectations or not. If it is not performing as per the expectation, then there is a need to modify the design, go back, modify, simulate and test the cycle till you get the exact design. So, this is the way we can implement the basic design loop. Whereas, there are few more steps those are required if you have to design an IC. Now, while designing an IC, we need to add synthesis tool. In addition to that, once synthesis, simulations and timing behavior are tested, then we can go for really implementing into the IC by using optimization and routing tools. So, this is physical mapping of the devices. The available resources could be mapped, tested once again for the timing, and then you can get the desired system. So, this is a complete flow that we require for designing a digital IC. So, I think we have covered the basic things that are required for starting the course VHDL and Verilog. In the next session, we will be talking about the VHDL and Verilog basic tools, as well as we will learn about the different models of implementing the digital systems. Thank you.